Assalamualaikum warahmatullahi wabarakatuh, and good afternoon to all students. Okay, so now we are going to learn our new topic, which is design buildings to resist wind loading. To design the building in resisting wind loadings, okay, you must have the clause MS1553 2002. So here are the clause that you need to have. Here are the Malaysian standards that you need to refer throughout this design wind loading. As for the learning outcome, okay, at the end of this lecture, students should be able to discuss the physical nature of wind in order to quantify the magnitudes and direction related to the design load, know the definitions of the basic wind speed, be able to describe the main feature which influence the wind load imposed on the structure, be able to analyze and determine the wind pressure, which is the main important part in this topic. Number 5, be able to identify the external pressure coefficients, be able to design the enclosed building for base shear and base overturning moment, internal pressure and roof, and also be able to design the signboard and hoardings. Okay, so there are two things that you need to design. The first is the enclosed building, and second, you should be able to design the signboard and hoardings. Wind pressure. Okay, so before we straight go to the examples, I will explain a little bit about what is wind pressure, because you need to understand the wind pressure itself. Okay, so this is the plan view of a buildings. So you can see this is the buildings, which is a rectangular in plan and subjected to the wind speed kinetic energy, okay, because it's moving, okay, and then it will cause a dynamic pressure and change to potential energy. So what is wind? Wind is the movement, okay, it is a movement of air mass, okay, because it is comprises of an air, and the moving of air mass processes a kinetic energy. So when the air movement is stopped by a structure, so meaning that this is the air mass, okay, movement travel to a certain distance and hit the structure, which is being stopped by the structure, okay, so the kinetic energy, which is moving, you have the kinetic energy, is converted to a potential energy. So this is the wind, it is converted to the potential energy, which exert a dynamic pressure, Qs, on the external pressure of the structure. The dynamic pressure, okay, is the wind load. This is the pressure that acting on the building is what we call the wind load. Usually, the wind load is measured in unit Pascal or kilopascal, and usually acts normal to the wall. So it is normal to the wall, the angle, roof or other surfaces of the structures. Alright, just to let you know that earlier we say that the movements, okay, the movements of wind will change. So meaning that when you have the movements of wind moving, okay, moving, it is in carrying the air mass, okay, carrying air mass, and then when it hits a wall of the building, okay, when it hits the air mass, which is initially in the kinetic energy, will turn into a potential energy, okay, will turn into the potential energy. However, not all the kinetic energy, okay, is converted to potential energy. the degree conversions depends, meaning that the degree of the conversions kinetic energy to potential energy is depends on the names what we call as the aerodynamic shapes. Okay, so the conversions here, the conversions of kinetic energy to potential energy is depends, okay, it is depends on what we say is it is depends on um, aerodynamic shape factor. Okay, so the more aerodynamic the structure is, the less the energy conversion, okay, and thus the smaller dynamic pressure on the structure. So if you look, we know that the this is a good aerodynamic shape factors. Okay, this is good aerodynamic shape factors. So when the wind pressure, which is acting here, and then hit the wind, hit the wall, so the wind will be dispersed. Okay, the wind will be dispersed to a different angle. Okay, this is, you can see it will disperse. Okay, it will disperse to the certain angle because it has a very round smooth surface. It has a very round smooth surface that it helps to disperse the wind and travels to the other directions. Okay, so more aerodynamic shape, smaller dynamic wind pressure. More aerodynamic shape, smaller dynamic wind pressure. So but if you look at this, okay, if you look at this is the types of plan view structure where we can say it is less aerodynamic shape because it is very sharp at the end. Okay, and when the wind comes, okay, try to suck here a little bit, and it has to get this, okay, and it will go straight here. So the dispersions of the wind load is not as smooth as when you have a good aerodynamic shape factor. So in this particular case, less aerodynamic shape, higher dynamic wind pressure. Alright? Therefore, the external pressure coefficients, okay, account for the degree of conversion for KE to PE. So these aerodynamic conversions is accounted when you wanted to convert the kinetic energy to the potential energy. So this degree of conversion will represent for coefficient factors what we call as CPE, CF, CPN. So the conversions of kinetic energy to potential energy will be represented by coefficient factor. Okay, so in addition to the normal pressure, meaning that we have the normal pressure, here is the normal pressure which is acting normal to the pressure, wind also induces frictional forces called frictional drag forces. Okay, so when the wind acting normal is not stopped there, you can't stop the wind, so the wind will go disperse, and when the wind parallel to the normal pressure, it will create a frictional drag forces. Okay, frictional drag forces. The frictional drag forces is represented by a coefficient CF, represent for the frictional drag forces, and this also accounted for the degree of conversions from KE to PE. Okay, from KE to PE. As mentioned earlier, okay, the not all kinetic energy is transformed to the potential energy. So those does not transform, you need to get into the consideration what are the coefficient factors. So apart from the earlier mentions, another coefficient factors is the frictional drag forces. When the surface parallel, okay, this is the surface parallel is when the surface parallel, the wind, okay, is long, is long and has corrugations, so the frictional drag forces will be larger. So meaning that if you have a very rough surface here, okay, compared to a glass surface, let's say here you have a very rough surface, for instance, like you have a corrugated web or something like that, or if you have a corrugated surface, okay, that is corrugated surface, acting the wind acting on the corrugated surface, or you have a very smooth surface, for instance like glass, the wind. So the frictional drag forces for the rough surface or corrugated surface will be higher compared to when you have a very smooth surface like glass. Okay, so that's what I'm trying to say. Okay, so there are many factors that influence the external pressure coefficients and drag coefficients, which means drag coefficients and external pressure coefficient as mentioned earlier. All these factors are combined together and collectively called the aerodynamic shape factors. So just to summarize, okay, a mass convert to kinetic energy to potential energy, and not all the kinetic energy is converted to the potential energy, and it is because you have aerodynamic shape factors. If you have a very good aerodynamic shape factors, then your have a smaller dynamic wind pressure. But if you have less aerodynamic shape factors, then you have a higher dynamic wind pressure. So the factor coefficients that need to be accounted for when you calculate the kinetic energy transformed to the potential energy, you need to consider the CPE, CF, and CPN, and at the same times you also have a drag forces, frictionals, where you call it as the F. So all this together we call it, which is CF, we have CPE, we have CF, and CP, and so all this is what we call as a CFIC, which is the CFIC is represent for the coefficients, okay, coefficients for aerodynamic shape factor. Okay, apart from having the contribution from the drag forces or the aerodynamic shape factors, okay, in addition, the dynamic wind pressure can cause vibrations in the structure. Okay, so when you have a tall buildings, okay, when you have a building which is tall and it is subjected to the wind forces, so if the wind is too high, the wind pressure is too high, so it will cause this building to vibrate. So it can vibrate, okay, at some point it will vibrate, and it also can vibrate in another angles and so on. So the vibrations, okay, on the structure, which in turn interacts with the wind to cause additional dynamic stresses in the structures. So you may have like the structures like this, it will vibrate. Okay, so because of that, you also need to calculate the dynamic stress, or what we call as the dynamic amplifications. And dynamic amplification is particularly important in flexible structures whose natural frequency is less than 1 hertz. Okay, so if you have a buildings and the structure is less than 1 hertz, so it means that the building is susceptible to a higher resonance, or the building is susceptible to higher dynamic effects. Okay, so therefore for those buildings who have less than 1 hertz, these structures are called wind sensitive structures and are accounted for using dynamic response factor, what we call as C dynamic. Okay, so does the design wind pressure is given by kinetic energy. Okay, the design wind pressure, we wanted to know what is the wind pressure. This is your building. We wanted to know what is the wind pressure. Okay, so the design wind pressure is equivalent to kinetic energy times with the aerodynamic shape factors times with the dynamic response factors, where half of mass of air times with design wind speed squared. Alright, whereby the design wind pressure is measured in unit Pascal. You get this? Okay, this is the design wind pressure. So this is the ultimate objective when you wanted to calculate the pressure acting on the buildings. So it is also highlighted that the minimum wind pressure that you calculated here must not be less than 0.65 kilopascal. Okay, to not wasting our time, I will go through with you all the clauses that we need to refer in designing the in designing the structure, in designing the wind pressure. However, I will go through the clause together with the examples. So from now on, make sure you have the MS with you, standard, calculators and papers, and please take notes on whatever have been mentioned throughout the examples.